Good morning. Thank you for joining us and welcome to our weekly e-learning session. My name is Dwayne Henderson. I'm a member of Cree Lighting's training and education team and host of our e-learning series. For those watching live, happy Friday. Quickly about the session, once we get rolling, we'll have roughly 15 minutes of content. Our presenter will be available for Q&A at the end of the session. And although the attendees are muted, we do encourage you all to use either the chat or the Q&A box to ask questions. Feel free to type those during the presentation and we'll circle back and answer those at the end. Today's presentation is entitled Mid or High-Powered LEDs, Should We Care? And to help answer that question, I'd like to welcome Joey DeSena. Good morning, Joey.
Good morning. How are you doing?
Great. Hey, before we get started, can you quickly talk about your role in the business?
Yes, quickly. So I'm an LED systems engineer in the R&D for Cree Lighting. Currently with indoor products, so I've worked on outdoor in the past. And so what that means is that I help with designing literally the LEDs and boards and sometimes the optics that work in our new products.
Perfect. All right, great. Well, let's get started.
Great. So mid high-powered LEDs. If you're someone who's been familiar with Cree Lighting for years, you might remember that once upon a time we were very much all aboard the high-powered LEDs train, especially when we were a part of Cree Incorporated. That's kind of their bread and butter. And that was kind of a feather in our cap. In recent years, however, mid-power LEDs have really burst onto the scene in a big way. And so there's maybe some questions that might be out there about, well, what's better? And so hopefully this presentation will help answer that. So if the slide goes forward, there we go. So I'm going to go more in depth on this in the next couple slides, but just a really quick overview and how it pertains to Cree Lighting. High-powered LEDs, as you might suspect from the name, typically made from more high power density materials, kind of all around from the chip up. And Cree Lighting has been using these since the beginning, again, specifically Cree LEDs. And they're best for applications where good thermal conductivity is important and you need some high power per LED. And typically they fall in the 1 to 30 watt range. That means 1 to 30 watts of DC is run across each LED. And they have a higher cost than mid-power. Mid-power is something that Cree Lighting has been using in more products since around 2013, 2014, which kind of also mimics the wider lighting space, and typically made from lower power density materials. And they're best for applications where cost is more of a concern and power per LED doesn't need to be very high. And typically that's about 0.2 to 1 watt. So high-powered LEDs. Now, high-powered and mid-power work off the same basic principle, which is how most LEDs work. I'm going to probably use the word typically a lot because there's always exceptions to the rule. But the typical white LED has a blue pump or die or chip, whatever you want to call it, that has a blue peak that comes up in around the 450 or so nanometer range. And then there's a phosphor that is put over the top of the chip. This one from this chart is a yttrium aluminum garnet doped with cerium, I believe, phosphor, which is a very common one, that basically takes some of those blue LEDs that are being emitted by the chip, kind of absorbs some of that energy, releases it as heat, and then releases a lower energy photon, which in this case would be green, yellow, red. Combine all this together, you get a good approximation of white light. I say good approximation. There's typically some gaps in here, like you can see right here. If you had a perfect approximation, it would be completely filling out that spectrum. It would be 100 CRI, which is great. Difficult to achieve, but we can get pretty close. So changing what you have in the phosphor formula, for example, or even the chip, you can get different color temperatures, you can get different CRI. All of that really depends mostly on the phosphor and the chip being used. Now, as for differences, for a high-powered LED, typically it's made with a high-power density die, as I said before. For Cree Lighting, again, coming from Cree Incorporated, typically we would use a silicon carbide. It's a very high power density. I want to say off the top of my head, it's something like 6 times the thermal and electrical conductivity of, say, a sapphire, which is a typical medium-powered LED dye. Now, this is great for, as you might imagine, high-power applications. And Cree Incorporated, again, is using that in their high-power, and RF applications. So it's a technology that is well-suited to that kind of application. But that's not where all the fanciness ends with high-powered LEDs. We also have typically ceramic packages. Packages meaning the substrate that the actual LED chip sits on and that we solder to on a board. Ceramic being a good conductor of heat. Again, great for those high-power applications. And typically, again, there is a molded silicone lens that is placed over the die in order to get maximum extraction out of the LED. You would actually get less light out of that LED if there was nothing on there, rather than a properly designed silicone molded lens. As you might expect, all of this adds a little bit of cost to the whole production process. So the design advantages of these high-powered LEDs, high lumen per watt if you need some high-powered density, high light output. I think most people remember a few years ago in the Super Bowl, if you're a sporto, that there was problems with the lights. These were not LED lights during Super Bowl 47, and they kept having problems with them shutting off. And then they'd have to wait 15 to 20 minutes for them to warm back up so they could come back on. Now, LED lights, of course, have instant on, instant off. So this is the kind of application that would be perfect for a high-powered LED. And in fact, if I recall correctly, the very next year, they made sure that they had LED lights at that Super Bowl. So it's a high power density, great thermal conductivity, as I said before. And you have a better opportunity for optical control. Again, with this molded dome, you're able to extract more light, and then you can have, and just to be clear, this is not a Cree lighting fixture, but it is very easy to point out what I'm trying to say here, is that you can have these molded optics that go over a typical high power LED in order to extract even more and get that light exactly where you want it to go, kind of like in the spotlight, or the nano optics feature that Cree lighting has in several of our outdoor products. If you want a large amount of light coming out and you want it directed in a very specific spot, like if you have a street light, you don't want light being cast behind the pole into someone's yard or up into the sky. You want it on the street. High-powered LEDs are very good for that kind of application. And also, typically, they have a very long life because of that high power density if you're running them correctly. I have it noted here, an L70 of greater than 100,000 hours. If you were here for a previous e-learning session from John Vollers, he went over some of the application or some of the terminology and testing methodology for lifetime of LEDs. L70 meaning that LEDs slowly lose light output over time. They emit less. So L70 is the time it takes for an LED to reach 70% of its initially rated light output. 2,000 hours is pretty great. That you're talking, again, with typical use, a couple decades. So it's pretty good. Now, design disadvantage is a big one. They're higher cost. Each one's going to cost more. That ceramic's not cheap. That molded end cap, and of course, the substrate or the chip are all higher cost than a mid-powered LED. So these are typically valued for, like I was saying before, exterior products, solutions where optical control is very important, and when you need high light output. Now, I'm talking about some mid-powered LEDs. These are, again, they emit light, white light, in the same basic principle. You have a phosphor-converted blue light dye. However, starting with the dye, it's made with a lower power density dye. I said before, sapphire is a very common one. I believe it's the most common in the market. It's a technology that's been around since the 60s. So a lot of people, a lot of companies know how to make it in quantity, which makes it lower cost. And it's a very common material that's easy to produce. Typically, the package itself is plastic, not ceramic. That, as you can imagine, is also lower cost. And it's kind of formed into pool, again, typically, into kind of a pool that you can mix the phosphor and encapsulant, silicone encapsulant together and just pour it in. You don't have to spray the encapsulant on and then mold the dome onto it. It's just this kind of a slurry that you pour in there. That is, of course, a more cost-effective method of making this LED, but also you can have little hot spots of phosphor in certain parts of the pool, and it might not be quite as even in what kind of what color photons it's spraying out everywhere. If you get, a little too cost-cutting in your measures of making it, so it's something else to watch for. And again, it's usually rated up to about 1 watt of input power per LED. There's multiple reasons for that. A main one is that the plastic package is not designed to transfer heat very well. And so if you keep running it too high, the heat in the system has nowhere to go. It will degrade the lifetime of the LED itself, and you might get something closer to 50,000 hours or less. Again, if you're not running it in a correctly designed system. So that's a lot of caveats. What are the design advantages of mid-power LEDs? Well, you can combine them because they're low power and they're much lower cost. A high power LED can be on the order of $1 or so. A typical mid-power can be on the order of a few cents. So that much lower of a cost, you can use many more of them, and you can combine them to form many fixture shapes. Again, none of these are Cree lighting products, but they're good for illustrative purposes. When you're allowed to use multiple mid-powered LEDs, you can put them kind of all over in these, lamp replacements, or in a T8 lamp replacement here, or in just a 2x2 troffer here, where if you want a low glare solution, you can just put hundreds of LEDs, mid-power LEDs, on these large boards, and each one's only emitting maybe a few dozen lumens. So it's not one big bright LED that might glare right into someone's eye. And they require only minor heat sinking because each LED is not designed to be this big, massive power and heat sink. You don't necessarily need a metal core printed circuit board. You can get away with something like fiberglass because they're, again, if they're designed correctly, not going to get too hot. So that's something that you can, again, go with less expensive other materials in the product. Now, the disadvantages are all things that are important to keep in mind. Again, as I noted before, there's a typically lower lifetime because that plastic package is not designed to go too long. And they're not suited to high temperatures. You want to keep that LED in operating conditions less than around 85 C. Again, typically, you can find plastic package mid-power LEDs that use more expensive, more robust materials, but more often than not, you're going to want to keep it under 85 C. There's less opportunity for optical control. As I said before, and you note here, you have this pool of encapsulant and silicone. You're going to have light kind of bouncing wherever, and you're going to lose a little bit of light going off these sides. It's not as nice extraction features as you have that molded dome. And so light kind of just spills out in a bit of a Lambertian distribution that's not terribly controlled and hard to add additional optics to and get good results. And I already said before that you can have that short lifetime if it's not designed correctly. So where are these typically used? Indoor products, low lumen, relatively low lumen, low glare products, and solutions where optical control is less important. But if you want kind of just to create a very even illumination, and you don't need that any kind of like that nice Lambertian distribution, but you don't need direct light right here to this spot right now, that's much better for mid-powers. So getting to the actual question, the whole point of this presentation is, should we care? The answer is not really. And the reason for that is because system design drives the best solution. As mid-power LEDs have come more into their own in the past 5, 6, 7 years, they have found their own niche in a lot of products, again, mostly indoor. But the flexibility that we have with Cree lighting to decide between a high power LED or a mid-power LED means that we have unconstrained product design. We still buy a lot of and use a lot of Cree LEDs. We were with them for a long time, but we have the flexibility to use other people's LEDs, other companies' LEDs, and we do. It all depends on that product design. And as the technology continues to evolve, we will keep this all in mind. This is a lot of what I do, is trying to, in my job, is to figure out what's the best LED for a given solution, right? So here are some examples of how these different types of LEDs work better in different products. We have the Cree Lighting XSP as a long-serving street light in our portfolio. This is 10 LEDs. It's just 10 LEDs with nano-optic features, because you can control where the light goes really well. You can get upwards of 20,000, 24,000 lumens out of that. But a Cree Lighting ZR Troffer, currently, we use a lot of mid-power LEDs, maybe on the order of 100 or so. And that creates a nice, relatively low glare fixture for maybe a 4,000 lumen output. And then on the other end, just because you're using a mid-power LED doesn't mean you can't get creative. The Cree Lighting Cadient, which we have launched recently, it's kind of a skylight looking fixture, uses 6 different types of mid-power LEDs, more than 500 of them, in order to create all sorts of different combinations and this lighting experience. You can have a cloudy sky, you can have a blue, bright, like sunny sky. You can have on those sun panels on the sides, it'll be a nice bright midday sun reflection or something more akin to a sunset or a sunrise. And because of the design flexibility of those mid-power LEDs, we're able to achieve that. So keeping all those requirements in mind, you can pick the correct LED for a given design requirement: light output, optical needs, indoor, outdoor, and of course, anything like an industrial design consideration, which something like the Cadient definitely uses well. And that is the presentation. Thank you.
Perfect. Thanks, Joey. Just to remind the audience, we are now open for questions. So if you do have any questions, please go ahead and submit those. We did have a question about a comment that said 85C is 185 Fahrenheit. What environmental temperature does this convert to when taking into effect the heat generated by the chip set on the ID power LED? You understand the question there, Joey?
I don't know if I caught the last couple words there. ID power LEDs?
Yeah.
If I'm understanding the question correctly, like what do we? I'm going to assume that's asking like what kind of temperatures should we expect to see maybe in a typical kind of fixture? Mm-hmm. If that's incorrect, please let me know, but I'll just go ahead with that. So for example, for a typical indoor troffer application like the ZR, that's rated for a 35 degrees C ambient room temperature. And so we test to that, and for a typical ZR troffer, the LED case temperature gets to maybe 60 degrees C. So not very much. Like I was saying before with those mid-power LEDs, they don't get very hot because you're not running each one with too much power. So it doesn't become this immense heat trap. Just being near to the pan, the metal pan, is enough heat sinking that's required. For more high power LEDs, they're typically okay to run pretty well above 100 C. And that's why they're also good for outdoor type applications where environment can be very different. You want to make sure that your street lights that are running in Phoenix, Arizona don't randomly fail because it's too hot, for example.
Yeah, and we do in situ temperature testing as well. So a lot of, our evaluation process is really looking at these products in kind of a typical environment and designing the robustness of that. All the devices we're really using, including the LED, to be able to withstand and perform really well in those types of applications. Is that correct?
Oh, yes. Yeah, that's a typical, that does a specific test that we run for every product as it goes through R&D, is some in situ testing. And we also do some extreme reliability testing as well. Power cycling, temperature cycling from say -40 to +55 C, high humidity 55 C as well. Just in order to make sure we extend, even though it's not rated to run at 55 degrees C ambient temperature, we want to make sure that there's some headroom and that there's nothing strange that might break down in the system. So we do lots of testing to make sure that even if we use, for example, mid-power LEDs, that they are suited to the cause.
Yeah, there's another question that's come in about low-powered LEDs. So I know we talked about mid and high, but they're asking what free lighting products utilize low-powered LEDs. I don't know if we have any that do, and do those LEDs actually produce longer light? But I think I've heard of them like in traffic signals. But are we using any low-powered? And is the industry that you're aware of using low-powered LEDs in lighting solutions?
No, and it's kind of tricky. I think a lot of LED manufacturers kind of conflate that, like low. Like I don't think they like using the term low because it sounds bad, maybe. And so a lot of low power LEDs, you might consider low power LEDs are actually mid power LEDs and vice versa. If you want like an extreme low power LED, that's probably not suited for lighting conditions. Even the LEDs we use, like for example, in the Cadient, they give off at certain settings only a few lumens per LED, which is pretty low. I mean, you don't probably want to go too much lower than that. So it's kind of, I don't know if it's marketing materials or something else, but typically mid power and high power are the two names in the lighting game that are used. If that answers that question fairly well.
Yep. There's another question about to get better color rendering out of the LED chip, what changes in the manufacturing process are required to do that? You want to talk a little bit about that?
Sure. So for better, like for example, CRI or TM30, you want to mimic basically a black body curve as well as you can. You want to mimic effectively the sun or an incandescent light. And so you want to have as much full of that spectrum as you want. Now, as I noted before, if I can go back real quick just to have something to point to, like we have this gap right here. If we had just a nice full spectrum from say 400 to 700 nanometers, that would be pretty darn close to 100 CRI. So what can be done on the chip level and the phosphor level to fill in those gaps is what's necessary if you want to get closer to that. You could have a lower wavelength blue chip, maybe something that's violet or something closer, maybe approaching UV. You could have multiple types of phosphor, additional types of phosphor that will make the chip or the component less efficient, and that's going to be your real trade-off. Is that all these additions to make better color rendering are effectively usually going to make your end system less efficient. But that's the trick, is you want to fill up these gaps down over here as much as possible. Something else you can do. I mean, one of the early ways to create white light was like RGB, red, green, blue, literally different LEDs mixed together in a system, and it makes white. And so the problem with that is that you have peaks, right? You have a blue peak, you have a green peak, you have a red peak. So it looks like white, but actually the color rendering was pretty poor. But you could have multiple types of LEDs that have different phosphor systems in order to cover the whole spectrum. There's lots of ways to get around to filling out that color rendering. The question really is, are people? It's for specific, as I'm sure you know, applications where that's needed and where maybe power electricity savings aren't as important typically.
Yeah, all things being equal, it's the higher the CRI, the more difficult it is to have equal efficiency, right? Unless you make changes another area. So I think that's about the way we look at products. Is you kind of look at the system and what's the application, what's the value that people are looking for, and then you can design systems that have high CRIs, or you can design systems that have really high efficacy. Hey, I'm sorry. Go ahead.
I was just going to say, I mean, and that's something that's out there on the market from multiple manufacturers. I've seen and tested myself high 90 CRI LEDs. Again, it's just a question of, is that trade-off for lumen per watt worth it?
Yeah, kind of getting back to the question of life, and I guess a lot of this stuff is going to be determined by how you treat the source, whether it's a mid or high powered LED. So the life question or lumen maintenance, probably a better way of looking at it. I assume I can get similar results using a mid or high power LED.
Similar lifetime results on a mid-power,
Yeah,
high-power LED?
I know you talked a little bit about the mid power, like it might have been a little bit less, but is that kind of a function of how you're treating it, or can you talk a little bit about that?
Yeah, you can get close. You can get similar types of lifetimes if you're treating the LEDs well. If you have a mid-power LED and you're running it relatively very low power or just low power, so it's really not getting hot at all. You can extend the lifetime into 100,000 hours or plus. I've definitely seen that before. And you can dramatically shorten the high power LED if you're pumping more power into it that's really designed to have like 40 watts or something crazy like that. So it's kind of, it depends on the guidance on how they're supposed to be used and how they're used in a system. So yes, so all that long answer done shortly is yes, you can have mid-power LED systems that approach the lifetimes of high-power LEDs, but you would probably have to take into consideration that better heat sinking and stuff like that in order to approach that. And typically, at least, again, there's typically again, if you're using mid-power LEDs in a system, part of that reasoning is for cost considerations. So that would kind of offset the whole purpose of using the mid-powers. Maybe not completely. It's probably still going to be cheaper than using some high powers. And again, I'm mostly thinking for indoor products. You would not really want to use a mid-power LED for an outdoor product. Trying to get 24,000 lumens out of mid-power LED system is going to be kind of insane. I'm not saying it's not possible. It's just at that point you might as well use high power because it's going to be probably insanely expensive. So.
Yeah. Hey, last question, and then I don't know how much we can answer this because it really kind of relates more to Cree Incorporated, which again we're not part of that business any longer. But somebody had mentioned that they heard that Cree Incorporated was one of the companies that was moving towards U.S. LED chip manufacturing. Is that something that is kind of a goal of the industry at all? I guess talk more in general terms, not because again we're not part of Cree, we can't really talk about what they're doing, but is that something you're seeing in the marketplace? I mean, we're using multiple chips, or is that something that you're not really seeing?
So just to clarify the question, like, are we seeing more of a move toward U.S. like stateside chip manufacturing?
Yes.
I mean, yeah, you're right. I mean, I can't say. I mean, because I literally don't know what Cree Incorporated is doing. I know that their silicon carbide chips have always been made in the United States. That's part of their secret sauce. I don't know. Yeah, I don't know what they're doing now with that, though. I will say, particularly due to tariffs, obviously, I'm seeing a lot more LED manufacturing outside of China, but still in Asia. So Japan, of course, Taiwan, South Korea, Vietnam. It's expanding. I don't know about stateside necessarily, at least not yet. But that's what I've seen.
Okay, perfect. All right, we want to go to the last slide. I will close up shop. I do want to thank Joey again for his time and for the great presentation. I also want to thank the audience for joining us. Looking ahead for the next couple of weeks, next Friday, we'll talk about optics. We've now covered drivers. We talked about the LED, and then kind of the third part of the trilogy will be talking about the optical control of these sources. So that's next Friday. And then the following Friday, August 7th, we'll talk about understanding distribution types and their application values. So looking at kind of what you see on the spec sheet, what does it mean, where do they get applied? So with that, as a reminder, if you have any questions, feel free to reach out to me. Again, all the content is being recorded and posted on our YouTube channel. So if you've missed the session, feel free to kind of check in there. With that, again, thanks everybody for joining us and enjoy your weekends.